Okay, well, we've seen Armstrong's axioms or rules where we can do derivations on functional dependencies. Here's a couple of more useful mechanisms that actually eventually lead on to the stuff that we really want to talk about. But these are, if you like, prerequisites to the discussion of normalization. Okay. So, generally we're dealing with a set of functional dependencies. Functional dependencies look like this, where both the left and right hand side can be sets of attributes, but if we want, we can just think of them as individual attributes. Alright, so given a set of FDs, functional dependencies, how many new dependencies can we derive using things like Armstrong's rules? Well, for a finite set of attributes, we obviously can't just generate an infinite number of functional dependencies, so there's going to be a bound on the number that we can generate. If we keep applying the rules and we keep generating new FDs, eventually we're going to reach a point where it doesn't matter what rules we apply, we're not going to generate anything new. And that is generally called a closure. So we start from a set of functional dependencies, we derive, and eventually, doesn't matter how many more derivations we try to apply, we end up with the same set of functional dependencies. Alright, well, if we can generate the maximum set of functional dependencies, then we can solve two interesting questions. So one, we may be interested in knowing whether a particular functional dependency can be inferred from an initial set of functional dependencies. And the other thing that we might be interested in, if we've got two sets of functional dependencies, are they equivalent? And obviously two different sets of functional dependencies. Alright, so for the first question, is a particular functional dependency derivable from F? Well, we simply compute all of the possible functional dependencies that we can infer from the starting set, and if it turns out that somewhere along the line we generate X determines Y, then we know, obviously, that X determines Y is derivable from the original set. What about the question, are two sets of functional dependencies equivalent? Well, one thing we could do, if they are really equivalent, when we generate the closure of each of the sets, they should be the same. Okay, so if the two original sets of functional dependencies are equivalent, then their closures will be equal. Right, so in theory, they're interesting questions, and there we have a simple description of a method to solve them. Problem is that closures, sets of derivable functional dependencies, can be extremely large. So here's an example where our starting set of functional dependencies is that, and here's a whole bunch of functional dependencies that we could derive from those ones. So having a computation that involves a very large set is generally not a great way to do things. So it's generally not going to be possible to do a closure on a set of dependencies. But a trick that we can pull is to not compute a closure on dependencies, but a closure on a set of attributes. So given a set of attributes and a set of functional dependencies, we use the FDs to derive, if you like, new attributes, add them into the set of attributes, and when we can no longer add any more attributes, we've got an attribute closure. So here's an extremely simple example. We start from X, and we've got this dependency here, so that we can add Y to our set of, to our intermediate closure, if you like. All right, well, once we've got Y, we've got a functional dependency here that says Y determines Z. Therefore, we can add Z to our closure set. And once we've got all of the attributes involved, well, that's as far as you can go. So that's the closure of X is XYZ, the attribute closure. All right, so the nice thing is that clearly the size of this is going to be bounded by the number of attributes. You can't have a closure of X which is larger than the number of attributes. There may be a number of steps to get to the closure, but at least the size of the closure is bounded. All right, and here's, if it wasn't clear from the example on the previous slide, here's the algorithm that we use. So we start with a set of functional dependencies, a set of starting attributes, and the goal is to produce X plus. All right, so we assume initially that a closure is the set of starting attributes. Okay, so X plus equals X effectively is the assumption there. So remember, closure is a variable which we gradually expand and expand and expand until we can't expand anymore, and then we've reached X plus. All right, so we have a loop that goes until we reach a certain condition, and the condition is that we can't add more attributes, no matter how many rules, how many functional dependencies we look at. There's no more to be added. All right, so first thing we do, we remember what the current closure is, and then we start looking through through the set of functional dependencies. So these A determines B come from the set F. Probably should have written that there. And what we're looking for is any functional dependency where all of the attributes on the left-hand side already appear in the closure. And once we find such a dependency, since the things on the left-hand side determine the things on the right-hand side, we can add the right-hand side to the closure. All right, and if we run through, we do this for all of the functional dependencies, then we're going to increase the size of the closure. If it turns out that going through all of the dependencies, we don't add anything else, so the closure that we derive from this is the same as the closure when we started, then we know that we're done. So we can set done to true, and the while loop will terminate. But this is the critical step. We've got a set of attributes. We look through all the functional dependencies. We look for functional dependencies, all of whose attributes on the left-hand side are already in the closure. And then we add the right-hand side to the closure. All right, so going back to those original questions, how do we answer the question, is X determines Y derivable from an initial set of functional dependencies? Well, all we need to do is compute the closure of X using F, and if it turns out that Y is contained in that set, then clearly Y is derivable from X. All right, what about the question, are two different sets of functional dependencies equivalent? So what we can do is we can look at each dependency in G and determine whether it's derivable from F. How do we do that? Well, we can do that like this. And similarly, for each dependency in F, we check whether it's derivable from G. Once again, use that method up there. If this is true for all of them, then in some sense F implies G and G implies F, which implies that F plus equals G plus. So we're kind of building on this method up here. And another quite important question to ask: what are the keys of some table R where there is a set of functional dependencies on the attributes of that table? And basically the trick there is pick a set of attributes, compute their closure. If the closure produces all of the attributes in R, then the original set of attributes, which I've called K here, must be a key. So let's have a look at a couple of examples of that. So we've got a set of functional dependencies. Obviously the R relation is A, B, C, D, E, F, G, because all of those attributes are mentioned in the functional dependency. Alright, so let's have a guess. Maybe A is a functional, is a key. Alright, so to check that, we compute A plus. And so if we look at these functional dependencies, the only one that's relevant is this one. That allows us to determine, to add B to the closure. And in fact, that's it. So the closure that we produce from A by itself doesn't include all of the other attributes, so it's not a key. Alright, what happens if we take AB? And I think I actually meant, oops, better go back and fix this. I think I meant AC here. Taking AB and determining the closure of AB is just AB. So let's imagine that this is C and this is C. So is AC a key? Well, starting from AC, we can determine B, so we then got ABC. Since we've got C, we can also determine D. So we'd end up with the closure of AC plus being equal to ABCD. Now that still doesn't incorporate all the attributes, so it's kind of obvious that if we take A, C, and E, then we're going to derive all of the other attributes. So ACE is a key for this relation. Alright, what about this one here? A determines B, B determines C, C determines D. There's clearly some transitivity going on there. Alright, is B a primary key? So we compute B plus, well, B plus determines C, that adds C to the closure. And then using C, we can add D to the closure, but that's as far as we go. So we can end up with B, C, D. What if we start from A? Well, A plus, A determines B, add B to the closure. B determines C, add C to the closure. C determines D, add D to the closure. And now we've ended up with A, B, C, D. And finally, this example here, A determines B, B determines C, C determines A. So it looks, a little bit circular. Alright, so is A a primary key? Well, A determines B, B determines C. That incorporates all of the attributes, so yes, A is a key. Are there other keys? And this is generally the case, that you can find multiple keys for a given relation and a given set of functional dependencies. So in this case, we look at B, B determines C, so we add C to the closure of B. C determines A, so we add A to the closure, and we end up with ABC again, so we've incorporated all of the attributes. So yes, B is also a key, and obviously C is also going to be a key, because it determines A and then A determines B. So you can use attribute closures to work out whether a particular set of attributes is a key. Alright, so that's it for closures. What about minimal, minimal covers is what we're going to talk about. But basically, what we're interested in is if we can come up with a set of plausible functional dependencies for a given problem domain, and then we think about it a bit more, and we come up with a different set of functional dependencies. Are those two sets equivalent? And we saw how we can work that out. But then the real question that we're interested in is which of those two sets, F and G, is the best one to model our application. Well, obviously, anything that's modeling an application has to encompass the entire semantics of the application. And generally, we prefer our models to be as small as possible. So if F has 5 functional dependencies and G has only 2, then we tend to favour G. Alright, so if we can determine a bunch of candidate functional dependency sets, F, G and H, and we can work out that they're all equivalent because their closures are equivalent, then we could look at what F, G and H all look like, and we could choose the smallest one and say that's the best model for our application. So that's all very interesting, but it involves deriving or it involves coming up with sets of functional dependencies, then doing some calculation on them to work out whether they're equivalent. Where do the sets come from in the first place? So another approach is to take a set of functional dependencies and then use them to derive a smaller but still complete set of functional dependencies. And if our derivation approach is smart enough, it's going to produce the smallest set of functional dependencies, and we said that we like things to be as small as possible. Alright, so the minimal cover for a set of functional dependencies has to be equivalent. There's obviously no point considering if it's not. And now we require certain properties on the minimal cover. All of the functional dependencies have this form, and the right-hand side always has to be a single attribute. And obviously, if it's a minimal cover, we don't want to be able to make it smaller, or it's not a minimal cover if we can make it smaller. And potential ways of making it smaller could be getting rid of a functional dependency that doesn't actually add anything to the set of functional dependencies, or by deleting an attribute. Alright, so a particular functional dependency is redundant if we can remove it from the set of functional dependencies and the closure is equivalent to the closure of the original set. So get rid of D, end up with the same result. We obviously didn't need D. An attribute is redundant if we can find a particular functional dependency and modify it by removing an attribute. So this is what we're doing. So we remove the original functional dependency, we add in a new functional dependency which has one less attribute involved in it. And if the set that we get there is equivalent to the original set of functional dependencies, then clearly that attribute wasn't necessary in the particular functional dependency where it appeared. So we can get rid of that. So you can see what we're doing. We're making tweaks to the set of functional dependencies such that we're making them smaller each time, but still equivalent to the original set. Right, so here's an algorithm for doing this. Input is a set of functional dependencies, and the output obviously is the minimal cover. Alright, so it happens in 3 steps. First thing we do, we put the set of functional dependencies into canonical form, which basically means splitting them up so that they've all only got a single attribute on the right hand side. The next step, eliminate redundant attributes from whatever functional dependencies we can find that might have redundant attributes, and then we can start eliminating redundant functional dependencies. And having done all of those things, we've now reached our minimal cover. Alright, so look at all these individual steps in a bit more detail. Step 1, put the functional dependencies into canonical form. If we have a functional dependency that has a bunch of attributes on the right hand side, then we split it up so that we've got n individual functional dependencies that only have a single attribute on the right hand side. Okay, so that's pretty straightforward to do, and the other thing about these is that they're relatively straightforward computationally, so we can actually write methods to do this. In fact, I am describing such a method. Alright, next step, eliminate redundant attributes. So we look through the set of functional dependencies and we find a functional dependency that's got a set of attributes on the left-hand side. So we, in turn, for each attribute in the set of attributes X, we form a new functional dependency that has that particular attribute removed, and we remove the original functional dependency and add in the modified functional dependency. And then we do the check. So G is the new set. So we see if G is equivalent to the current set of functional dependencies. And if it is, G becomes the new minimal cover. And so FC is gradually reduced and reduced and reduced as far as possible, as far as we can eliminate redundant attributes. And finally, we can try eliminating redundant functional dependencies. So we look at each functional dependency in our current closure, and we compute a new set of functional dependencies without a particular functional dependency, and then we check is G equivalent to the current closure, and if it is, then we can remove this functional dependency altogether and end up with a new and slightly smaller cover, a new slightly smaller set of functional dependencies, and eventually, having gone through all of the functional dependencies, FC is finally going to be our minimal cover. So here's an example. We've got a bunch of functional dependencies. We've got a relation. All right, to put these into canonical form, the only change that we need to make is to split this functional dependency up so it becomes A determines B and A determines C. Well, having done that, we've already got A determines B as another functional dependency, so we only need to keep one copy of that. So we've still got 4 functional dependencies, but they're a little bit simpler than they were. Alright, then we start looking for redundant attributes, and really the only option is to look at this one because it's the only functional dependency with more than one attribute on the right hand side. And so we see what happens if we take B out. Then we've still got A determines C, and therefore we're going to end up being able to derive the original set of functional, or the closure of this particular set of functional dependencies without the B is going to be the same as the it's the closure for the original set of functional dependency. And having removed B, once again we've got two copies of the same functional dependency, so we only need to keep one of them. Alright, so now we look for redundant functional dependence. If we've got A determines B, A determines C, and B determines C, then it's kind of obvious that this really isn't necessary, because given A, we can determine C. So that functional dependency, which was obtained as part of the derivation sequence, is also now redundant. So we can finally end up with a minimal cover, A determines B, B determines C, from this original set of functional dependencies. So that's kind of useful, because we started off with a complicated set of FDs and we've ended up with quite a simple one. And with luck, and it's pretty hard to tell with this abstract view of things, but maybe this represents some critical information about the semantics of the problem. Alright, so closures and minimal covers are two useful mechanisms that we're going to use when we start looking at restructuring schemas to remove redundancy, which will be in a subsequent video. Okay, that's it for closures and covers.